Thank you very much for coming today. So today we have our Matthew Wright, probably the only guy that can challenge Craig Johnson hairstyle. So Matthew did his undergrad here at UNSW, and then he joined the organic photovoltaic group to do his PhD. He submitted his thesis a few months ago, and he's doing now the writing fellowship. So Matthew was quite kind to have two parts of his talk. One is a bit of overview about what is new in organic photovoltaic, and the second part will focus more on his work and his research. So please welcome Matthew.
Hello everybody. Firstly, thanks to Rob for doing all the setup for today, and to Ziv for the intro and all the organisation and stuff. So, as Ziv said, my name is Matt Wright, and I've just finished my PhD here at the University of New South Wales. Today, I'll be talking about organic photovoltaics, a technology overview. So, as Ziv said, today the presentation has two separate components. For the first part, I'll be looking at an overview of organic photovoltaics as a technology, and we'll look at some things like justification for organic photovoltaics. What are the advantages of this approach? We'll look at some demonstrations of recent deployment of OPV modules in the field, and we'll look at highlight some of the current challenges faced by the technology, and look at what's required to overcome some of these problems. So hopefully it's a pretty honest assessment of the technology. And then the second part, towards the end, we'll look at some of the research conducted here at the University of New South Wales. So we'll focus primarily on optimisation of the buffer layer within the cell, and also we'll have a look at a newish concept called the ternary blend organic solar cell. So when looking at an overview of a technology, particularly for a solar technology, probably the most important metric to look at is the efficiency. So if we have a look at the NREL efficiency table, organic photovoltaics is located down in the bottom right-hand corner with some of the emerging photovoltaic technologies. Now, if we zoom in, sorry, the resolution isn't great, but you can see for the closed triangles and also the closed circles, there's been, in recent times, a rapid improvement in the efficiency. When I started my PhD in 2011, the best efficiency for OPV was 8%, or 8.3%, and now the efficiency is at 12%. So during the course of my PhD, the efficiency has increased relatively by 50%. So the field of organic photovoltaics is pretty fast moving, as you can see. We've seen in the last couple of years the rapid rise of perovskite solar cells, for which the efficiency has increased even more rapidly than this. And I won't be neglecting perovskites. I'll have a bit of a discussion and talk about perovskites when we're talking about the fabrication techniques used for the solution processable cells. Okay, so rapid increase. Most of the high efficiency devices for organic solar cells use a tandem architecture, whereby we have two cells and they're connected in series. There's a company from Germany called Helium-Filled, who have produced a tandem solar cell with an efficiency of 12%. So here is a very rough schematic overview of their device. They have two absorber layers which are connected in series, and this technology actually uses a vacuum deposition rather than solution phase deposition of conjugated polymers. For this device architecture, one of the unique points is that the interlayers, or the buffer layers and the intermediate layer, are vacuum deposited from organic materials, but they're also doped. And that's one of the unique properties of this cell. So this has achieved an efficiency of 12%, but the fabrication techniques and the materials used are unpublished. So we can have a look at a few Nature papers of high efficiency cells which have been published. This one is an example from UCLA, and they also it's a series connected tandem solar cell. You can see the schematic up in the top left-hand corner. So they have the top cell uses a polymer called P3HT, which has quite a wide optical gap and absorbs in the visible, and then they use a lower band gap polymer for the bottom cell. So from the EQE you can see that on the left-hand side the top cell is absorbing in the visible and the lower band gap polymer is absorbing in the infrared region. The black and the red curves are very similar. They use a slightly different acceptor for the top, for the low band gap cell. So we can see from the JSC, or from the IV curve, the JSC for this device is about 10 milliamps per centimetre squared, and the VOC is more than 1.5 volts. And I've also got the NREL certified IV curve here as well. You can see the efficiency is 10.61%. The VOC is 1.53 volts. And the JSC is around about 10 milliamps per centimetre squared. So for the future, the JSC, that's a problem. The JSC is very low, 10 milliamps per centimetre squared. So for improvement in the future, multiple things that can occur. One thing that needs to happen is the synthesis of new polymer materials which can have broader absorption widths and can also achieve higher EQEs. You can see that the EQE values here are in the order of about 70%. But for the future, to improve this efficiency, to bump up the JSC, what needs to happen and what is happening is people are looking at synthesizing polymers which have broader absorption range and can have higher EQEs to allow for higher JSCs. So there are multiple companies at the moment which are looking into this aspect. Mitsubishi and also Toshiba are partnering with chemical companies with the aim of finding these new polymers which can have better absorption so that we can have a higher JSC for this tandem solar cell. I've got the next IV curve is from, I should mention that, yeah, these materials used in this paper from UCLA are all pretty common and commercially available materials. So for the future, synthesis of new polymers is required. I've got this IV curve from the most recent Martin Green efficiency table. And you can see that the red IV curve there, it's a bit hard to read, is from a company, Toshiba. So they've synthesized this new polymer material, and you can see the JSC for this device is almost 20 milliamps per centimetre squared. So nowhere near the range of something like the Pearl cell or a normal silicon solar cell. But the absorber layer for this device would be less than 500 nanometers. So achieving an efficient JSC of about 20 milliamps per centimetre squared. So this is an undisclosed polymer material, and it just highlights that this is what's happening in the field. People are looking at improving or finding new conjugated polymer materials which can have wider absorption breadths, higher EQE, so that we can have achieve a higher JSC. So that's a brief overview of the efficiency and where that is at. Let's now have a look at, I'll talk about some of the justifications for using organic photovoltaics. Why are we interested in studying this technology? One of the main properties which is desirable is that all the layers in the cell can be processed using roll-to-roll solution phase fabrication. And this allows for multiple advantages. One is that we can have, the technology can be very scalable. You can imagine if you're making these solar cells in the same way that you would make a newspaper, then it would be possible to have very high throughput manufacturing so that the technology would be very scalable. Additionally, because of the fabrication techniques, the energy embedded in the production of the cell is very low, and we'll have a look at some LCA analysis in a minute, which looks at that point. And additionally, one of the unique properties is that you can use flexible substrates which are lightweight, and additionally the photoactive layer can be transparent. So I have a couple of neat examples here. On the left-hand side is a semi-transparent organic solar cell. So with a high transparency, but still a moderate efficiency. So one application potentially for this would be in windows, to use semi-transparent coatings of windows of an organic photovoltaic module. And the one on the right is from MIT, and this is really an exploration of the type of cheap substrates that can be used. So they've made these solar cells on paper and also a stamp, which is sort of highlighting the fact that you can really use cheap, lightweight, flexible substrates for this when you're using solution phase processing. Now, let's have a look at some of the LCA analysis which has gone on over the past couple of years. Initially, when organic photovoltaics started, the device was fabricated on glass, and one of the electrodes was a conductive oxide, typically was ITO, and this material or this layer is coated by sputtering. So one of the initial points from the early LCA analysis was that the ITO, because it requires sputtering, in terms of the material inventory and the energies used, the ITO it takes up too much energy. So you can see from this LCA, they suggested that about 87% of the embodied energy from the materials comes from this ITO layer, which is coated by sputtering. So it was identified that this is a problem. We need to find an alternative to this ITO layer if we want to really have a cheap technology that has low embodied energy. So I've got a photo here from another LCA paper which shows an example of an indium-free thin silver semi-transparent front electrode. So this is to replace the ITO layer. You can see it's on a flexible sheet, and this is being prepared by slot die coating, which we'll actually have a little bit of a look at in a video towards the end of the presentation. So once that was identified, this problem was overcome, and now the roll-to-roll processing can occur by removing the ITO process. And so if you do that, if you see, so I can explain this one. This is related to the energy embodied using different fabrication methods. So the first one on the left-hand side, this pie chart is the same as the one from the previous paper. It shows that the inventory of the energy is very unbalanced and that the ITO was taking up a vast majority of the embodied energy. And so by removing that, and what we just saw, by removing the ITO and having a different semi-transparent electrode, then the energy embodied is significantly reduced, and you can see that the inventory, so this one doesn't have actually what it is, it was very small, but you can see that the inventory is balanced, so there's not one component which is taking up an unreasonable amount of the embodied energy. So by doing that, using this process which removes the ITO, the authors looked at projections of LCA and trying to calculate the energy payback time. And in doing that, they considered what is required, the improvements required for the future. And so they made a list of different assumptions which they categorized into two subsections. So one was a list of feasible assumptions, which they said included decreasing the layer thickness, increasing the width of the substrates, which for the papers we're about to see is 305 millimeters, about a foot, and also increasing the geometric fill factor. So they said that if we could do this, these are things that we think we can achieve. And they've also listed some challenging assumptions. So these include pushing to higher module efficiencies, significantly increasing the lifetimes, and also recycling and retaining the materials, for example, the silver, from once the cell is finished and the efficiency has dropped, you can take that cell off and recycle the materials. So the results from this paper are summarized in a table. So, sorry, it is quite small, isn't it? But I can read it out. So they have, for the process which contained the ITO, they said if the system efficiency was 2%, then the energy payback time will be 742 days, so a bit over 2 years. But by removing the ITO and having a solution processed semi-transparent film, suggested that the energy payback time was 129 days. And by looking at the parameter space of the multiple different assumptions that they've made, they suggested that if all of the feasible assumptions can be perfectly executed, then the energy payback time with a system efficiency of 2% would approach 1 month. And one of the main, highlights of this paper, and it was included in the title, was they said if they have a system efficiency, of 15%, and all of the challenging assumptions are executed and they're able to be achieved, then the title of the paper is that you could achieve energy payback time of 1 day, considering those very, very challenging assumptions. So that was the highlight of that LCA, and the data related to the energy production is all simulated. So this is not, they haven't actually measured this in the field. They've got a 2% efficiency and assumed the insulation values. So the actual energy generated is based on the model within the LCA. But now let's have a look at some of the recent, from last year, demonstrations of actual deployment of these modules which don't use ITO and are completely roll-to-roll solution processed. We can see how they've been deployed in the past year in the field. So the first paper we're going to look at is about a solar park which was installed in Denmark Denmark Technical University. And all of the processes used for those solar cells were solution phase, and it was all roll-to-roll coated using various printing and coating techniques. So this shows from the paper a photo of the different methods occurring. So one is printing the silver contacts, then screen printing one of the buffer layers, slot die coating zinc oxide, slot die coating the active layer, P3HT PCBM, the organic semiconductor layer, screen printing the top buffer layer, and then printing the electrode. So this is an overview of the roll-to-roll processes used during this paper. And they had, so it's rolled out sort of like a newspaper. It's a foot wide, and they roll it out on a rotary using these various different printing and coating techniques. And so for one of the investigations, they had the foil, the length of the foil was 700 meters, and it had 147,000 cells connected in series, and from that they had 100% technical yield, so there was no fault using this technique. And at the moment, this is sort of a pilot system, and at the moment they said that the fabrication speed was about 1 meter per minute from going from to the point where it's ready to be installed. Okay, so here's the final product. This is a nice picture of the solar park in Denmark. You can see the one up the top. They have what they call lanes, so these modules are 305 millimeters wide, and they have 6 of these, and they're 100 meters long. So for this case, they have this thing here, which is sort of an in-house built reel to install the solar cells, and the installation rate was about 100 meters per minute, so they could install and deinstall this 100 meter length in about 1 minute, and they suggested that in the future they could possibly achieve a rate of 300 meters per minute. So for this paper, they actually, as part of the supporting information, they have a YouTube clip of this installation, which is quite interesting. It's a short clip. I thought if you want to join me in the Jetsons-like future, we can have a look at this installation. That one, go like that, go like that, go like that. So this is that, yeah, I'll just let you watch it, you can see what's going on. So this is the 100 meter length being installed.
And after laying each one of these strips, do they reliably get 100% solar cell activity across it each time?
Yes. Yep. So the cells will degrade as a function of time, and I've got the stability data from this installation, but to be installed they required a 100% technical yield. Maybe it would have been faster if you ran faster. So that's the story. That's pretty cool. That's the installation from that particular solar park. So let's go back to F5. Oh no, not F5. Where are we? Sorry. Shift F5. Okay, so then that was the video. Now for the performance. This on the top is the IV curve of that entire park, and the performance of all the cells is 1.53% the efficiency. The PCE is power conversion efficiency, and it had a fill factor of 54%. And as I said before, we've also got the stability data. So they've measured the efficiency at periodic intervals across time, and you can see that for this installation, for this pilot system, the stability, it reduces. So this goes to 3,000 hours, and it's to about 80% or 70% of the initial measured efficiency. So they say that largely this just has the efficiency, but they said it was largely related to the fill factor and the VOC, which went down with time. Now, for the embodied energy in this park, as we said, all the LCA analysis before was from assumptions related to the energy generation. For this one, they actually have done the inventory and they've measured the output, and they've split. I've got this figure here which shows the embodied energy for the different components in the system. So you can see that the major component is the modules, and also the wood scaffold, the physical structure also takes up quite a lot of energy as well. So this is This was installed in Denmark, and for that case, it had an energy payback time of 277 days, that should be. And then they said if it was installed in southern Spain, where the insolation values are a lot higher, and assuming that the system performs the same for an installation in a different country, then the energy payback time would be 180 days. And that's related to actually measuring the system output, the energy generated, not an assumption of an efficiency over time. So yeah, these are scaled, assuming that it's installed with the insolation values in southern Spain, about 180 days. So the wood scaffold takes up quite a large proportion of the energy payback, or the embodied energy, and they say that the wood scaffold would last a long time. So if you were to deinstall after a year or two and reinstall, then the impact of the scaffold material would be reduced in the embodied energy. So this was the solar park, which was demonstrated or deployed last year in Denmark. This installation is a pretty conventional installation, I guess quite similar to what you'd have with a silicon solar cell, where you have a rigid structure and it's installed on a roof or in a farm somewhere, because the silicon solar cells are more heavy and rigid. But this group also took this a step further and thought about, this is the way to install if we want to have a large-scale energy generation system. But if we had smaller applications where we had to deploy something very quickly for perhaps an emergency response or something in a remote area, then what are the ways that this technology could be installed quickly? So they had two particularly quite novel examples. So this one was an offshore solar cell deployment, which was in a fjord in Denmark, and they used low-density plastic tubes. It was just tethered to the pier with ropes. So this was, I guess, highlights the fact that it's some of the unique properties, that it's really a lightweight material. The system efficiency was low, 0.61%, and they said that due to the installation there was possibility for rough handling, and they thought there could have been mechanical degradation because of that. And the second system which they investigated was a balloon, believe it or not. So here we have an example of a helium-filled balloon with dimensions 4 meters by 5 meters. So to support the weight of the cells, they had to, the balloon was filled with 16 meters cubed of helium, and it has an efficiency of 1.27%. So this is not a type of installation that would be used for large-scale deployment. It's more a demonstration that the organic solar cells are very light, and that there are multiple potentially very quickly deployable ways of using this technology. So for the embodied energy, they did a breakdown of the energy for the different types of installation, and the balloon installation they found was the embodied energy was very high, and it was largely related to the helium that you had to use. So not really a practical demonstration to compete with large-scale demonstration of power, but it was more a novel point to really demonstrate the lightweight nature of this technology and how flexible it is. So these installations that we've looked at so far for OPV have all had very low system efficiencies. And we've seen over the past couple of years a very rapid rise in the efficiency of the perovskite solar cells. Particularly, I think quite recently it was announced that the efficiency has reached 20.1%. And perovskites as a technology is compatible with solution phase processing and roll-to-roll processing. We've seen demonstrations of perovskite solar cells fabricated on flexible substrates. This is again from UCLA. And additionally, the temperatures used to anneal the perovskite layer are low, less than 150 degrees Celsius. So in principle, this perovskite technology is very much compatible with these roll-to-roll solution phase processing techniques. Some of the current challenges, one is related to the whole transport material. The currently most used one for the high efficiency cells is very expensive, and so one improvement for the future would be perhaps finding an alternative to that material, to find one that would be cheaper but also high efficiency. And there are also some issues regarding to the stability of the cells, and also the use of lead in the active layer of the perovskite film. So I was looking for papers about demonstrations of perovskites fabricated using these roll-to-roll techniques. And initially I couldn't find any, but I did find a video from the university, this Denmark Technical University again, which I think may have been the first demonstration, it was just published last week, of this, using this roll-to-roll, uses a slot decoder to process this perovskite layer on a flexible substrate, using these techniques which are required for this very scalable, low embodied energy technology. So I have that video, that short video as well, we can have a look at.
What you're seeing here is TU who is slot decoding lead iodide layer. This is the two-layer approach where you first apply the lead halide and afterwards the methyl ammonium iodide. And then you subsequently grow the perovskite layer over time. And the advantage of the mini roll coater in this context is of course that you can leave the layer there, leave the, should we say, the layer of excess methyl ammonium iodide and the lead halide, while the crystals grow at a given temperature. And you'll notice that all the processing is done here in a fume cupboard and under ambient conditions. There's an advantage in having a machine that is dedicated to processing one type of materials, or where we limit the use of one type of materials to only one of the processing machines, especially in the case of the lead-based perovskites, where at least in a country like Denmark, or probably most of Europe, where there is some regulations as to the use of soluble lead compounds, lead-2 compounds. And thereby only using one mini roll coater for lead processing, we know where the eventual spill or possible spillages can be, and we can somehow guarantee operator safety on other machines. So there is an advantage in dedicating one machine to certain processing steps.
Okay, so now we're getting ready to coat the second part of the perovskite photoactive layer, which is the methyl ammonium iodide layer. And getting ready to slot die-coat it on top of the lead iodide. And the two will react and form the perovskite photoactive layer. So, as you see, this brownish color is a completed perovskite photoactive layer. The MAI, the ammonium iodide in itself, is colorless, but when it reacts with the lead iodide, it gets this brownish color. This is a so-called two-step process where we coat the two components of the perovskite in two consecutive steps of slot die coating. I'll just roll back to coat the second line. And here you see on the left you see the lead iodide yellow line, and on the right you see the completed perovskite photoactive layer, brownish color. And to complete the solar cell stack, we need to apply a slot die coated layer of P3HT as a whole transport layer, and then a thin layer of P.PSS on top of that before we can print our electrode. Underneath our lead iodide we have a TET and ITO, and then we have a layer of zinc oxide. So it's in terms of an OPV, it's an inverted geometry.
There you have it. So I didn't realize how long that would take in this context. It was quite long, wasn't it? So there you go, a demonstration of using a roll-to-roll, a slot decoder to fabricate this perovskite technology. So it's happening already. They're using these techniques to fabricate this high efficiency layer. Now I have some late mail. I couldn't find a paper until yesterday. It's a paper published, or is in press at the moment, with Advanced Materials. It's a collaboration between a Korean university and the CSIRO, University of Melbourne. And they have done an investigation of the slot die coating process for the perovskite layer. I think this might be the first publication of this. And they actually investigated the use of nitrogen gas during the slot die coating for they call it gas quenched, for drying of the film. And so they had a bit of a look at the parameters involved, and they have IV curves here, which is a comparison of the white one is all slot die coated, and the black one contains spin coated layers. And you can see that using this slot die coating, it's still achieving the efficiency in the order of 10%. So it's happening now. People are using these roll-to-roll techniques and applying that in the context of perovskite solar cells. Now, briefly, we'll have a look at, so as I said, I wanted to mention some of the challenges. I want it to be a fair assessment of the technology. The efficiency of organic photovoltaics is low. It's much lower than all of the other, well, most of the other photovoltaic technologies. And so we talked about that a bit before, that requires a synthesis of new polymers which will have increased spectral breadth and higher EQE within that absorption range to lead to enhanced JSC. And one point to note is that to do this, it must be compatible with the printing and coating techniques. In the Solar Park paper, the authors mentioned that they used Pithra HD PCBM for that installation, and the efficiency was about 1.5%. And they said that they have investigated lots of other higher efficiency polymers, which in the context of a laboratory where using spin coating and evaporation techniques performed better. They found that the Pithra HD PCBM blend with the solution processing with the roll-through coating was, of all the polymers, the system that achieved the highest efficiency. So it's not just achieving high efficiency, it's also doing that in the context of the processing which is required. And then I'll also talk a bit about the stability. The stability, as we saw from the installation of the solar park for organic solar cells, is a major challenge which has to be overcome. So some of the reasons, well, particularly compared with silicon solar cells, which are just so stable, the mechanisms determining or causing the problems with OPV, some are related to chemical factors. So we have oxidation of the organic component and also of the electrodes. And particularly one of the buffer layers which is used is an organic buffer layer called P.PSS. And this is, if you have water or humidity, this layer will break down, and particularly the interface between the P.PSS and the ITO layer is a problem. Additionally, we have flexible substrates, so there's an additional problem with the mechanical stability. So we can have changes in the photoactive morphology, so the interactions between the donor, the polymer and the fullerene is not necessarily with time stable. We can have delamination occurring at weak interfaces, and also flexible stresses induced for these flexible substrates, mechanical stresses induced for these flexible substrates, particularly when the two layers have different thermal expansion coefficients, and some of the organic layers used have poor cohesive strength. So that adds another problem, that there's mechanical issues as well. So how can these be addressed in the future? On a laboratory scale, one of the early studies was related to changing the device architecture. So people have been researching what is called the inverted device structure. Initially, the devices were built on ITO. We had a layer of P.PSS, then our active layer with the organic components, and then normally aluminium was evaporated on top of this. And this caused multiple problems, and the stability was very low. One of the reasons was that the aluminium was not as stable as some other metals, and particularly if we have P.PSS from an aqueous solution as this buffer layer, which for the start of OPV research that was the case, that interface was also prone to degradation as well. So to overcome that, it's possible to change the nature of the buffer layers in the electrodes so that you can change the direction or flow of charge throughout the device. And I don't have an energy band diagram, but that will allow you to change the metal, so you can remove the aluminium, which was one of the problems because of its reactivity. And additionally, you can remove the P.PSS ITO interface. So on a laboratory scale, that was one of the first approaches. And then additionally, on a more larger scale, was the formation of what is called the International Summit on OPV Stability. So the purpose of this summit, or this regular conference, is that at these conferences they provide standard protocols for testing, and they undertake and report on interlaboratory studies, so round-robin studies where we have a standard cell, we test it at multiple different places. Like the example that I have here, there are 5 different places where they test it, so that they can try and standardize, have protocols in place for what the test should be, and try to understand how they can standardize and understand the testing so that they can further explore the mechanisms which are causing this degradation. So this is an example of a recent paper which has 5 different groups involved, one of them being CSIRO at Newcastle. So that's an overview of some of the problems faced by organic solar cells, and that concludes the first part of the presentation about an overview of the technology. I'll now briefly look at some of the research focused here at UNSW during the time of my PhD. So this schematic provides an overview of the device structure that we use in the lab here at UNSW. We have the devices are built on a glass substrate which is pre-patterned with an indium tin oxide layer. So this is an inverted device structure as we've just discussed. We have zinc oxide as the electron transport layer, and then we spin coat the photoactive layer. And so for this photoactive layer, we have a polymer and a fullerene within the same layer, because absorption in the conjugated polymers leads to not free charge but bound electron hole pairs, and as a consequence it's necessary to have a heterojunction in the photoactive layer. So we have these two different materials intimately dispersed in this photoactive layer, and this is the layer that we have primarily focused on, trying to alter this layer and understand what's going on. We then have a whole transport layer of molybdenum trioxide, MoO3, which is thermally evaporated, and then we have a layer of silver to complete the device. So this is an overview of the device structure. Firstly, we'll have a little bit of a look at the zinc oxide layer. So there are multiple different methods that you can use to fabricate this zinc oxide layer. We've been looking at a sol gel derived layer where it's solution processed, and you have a precursor material, zinc acetate, which is suspended in a solution. You spin coat it and then heat it, and the zinc acetate is converted to zinc oxide. And so there are multiple parameters that we've looked at for the deposition of this zinc oxide layer. One is related to the concentration of this precursor zinc acetate solution, or in the concentration in the solution. So we have some AFM images of the zinc oxide film. The first one is the bare ITO surface, so it's been cleaned and then straight to AFM. And we systematically varied the concentration of this precursor material in the solution. And we found that when you have a low precursor material or a low precursor concentration, you don't have a complete coverage of the zinc oxide layer over the ITO. And so you need to increase the concentration, and we found that the optimum occurred at 0.1 grams per milliliter, because that ensured that we could have a proper coverage of the ITO. And the devices that had a lower concentration than that were very poor. They were basically shunted because we had problems related to that interface. So that was the first step. We were looking at the different concentrations, and then to convert the zinc acetate to zinc oxide, there's a heating step. So we also investigated the heating step of this zinc oxide layer. So this is the Ftir spectra. So you can see that if we look at the low annealing temperature, 100 degrees Celsius, you can see that there's significant peaks present. So these ones at a wave number of about 1500 are related to the carbon-oxygen double bond, and also carbon-hydrogen bond at this wave number here. And you can see that as you increase the temperature, these peaks reduce significantly. And I haven't put it in here, but this peak at the low wave number is related to the zinc-oxygen bond. So this peak is emerging as the other peaks are disappearing as we increase this annealing temperature. And we also measured the XPS, which I haven't showed, which also suggested that as you increase the annealing temperature, the zinc acetate is more efficiently converted to zinc oxide. And so 350 degrees is almost, the carbon-hydrogen vibration is almost removed. And then to test the efficiency, sorry, the tables are quite small, I'm sorry about that. We found that the optimum efficiency was achieved for an annealing temperature of 150 degrees, which wasn't completely intuitive from the FTIR and the XPS data, because it showed that the higher temperature was related to more efficient conversion. So as we then did SEM images and found that with the very high annealing temperatures, we saw the formation of voids or pinholes in the structure. We thought that at these very high temperatures, if we induce these voids in the structure, it will have problems with the contact. So that's why we thought the highest efficiency achieved was at 150 degrees, because we did still have a large conversion of zinc acetate, but it had quite a smooth, uniform film. So that was the paper about zinc oxide. I'll now move to, as I said, the photoactive layer is where the main focus of our group lies. One of the problems, we mentioned the efficiency problem before when looking at the problems of organic photovoltaics. We mentioned the fact that the JSC is quite low. One of the problems is that the absorption of the conjugated polymers, it's not like an inorganic crystal like silicon. The absorption windows are quite narrow, and this limits the amount of the solar spectrum that we can convert, so that puts a fundamental limit on the JSC of the device, the photocurrent generated. One approach to overcome that problem is to use a tandem architecture, which is what we looked at earlier in the presentation, where you have two subcells connected primarily normally in series, so that you can have absorption in two different parts of the spectrum. But one problem is that the tandem architecture makes the processing more complex. So you're significantly increasing the amount of layers and buffer layers, and we want to keep that as simple as possible. So it would be ideal if we could find a way to increase the absorption breadth of the film whilst maintaining the relative simplicity of the processing, such that we only have one organic active layer within the device. And a way to do that people are investigating at the moment is to use a ternary blend. So I said before that we have in this photoactive layer one polymer material, which is the electron donor, and one fullerene material, which is the electron acceptor. But if we incorporate a third component, another polymer which has a complementary absorption, it may be possible to improve the absorption of this particular layer without increasing the number of layers in the stack. And so that's the idea behind the ternary blend composition, and our group has been having a bit of a look at the compositions for this structure. So we've been looking at a structure which has two polymers. One is called P3HT, it's the most commonly used polymer in organic photovoltaics. And additionally, we've looked at a polymer silicon bridge PCPDTBT, which has a narrow optical gap. And you can see from the absorption profile that it's quite neat. The absorption of the two materials is very much complementary. So if we could combine these two materials within the blend, we'd be able to have a broader absorption spectrum that film was responsive to. Now, incorporating this other material makes the morphology or the microstructure of the film even more complex, and will normally lead to a reduction, or it detrimentally impacts the morphology of the film. So it's important to understand the concentrations of the different materials of this three-component system in the blend, how they interact, and how can we optimize such that we can increase the JSC. So what we did is from literature, we set the ratio of the two polymers to 7:3, which was from a previous literature. And we investigated the ratio of the total amount of polymer to the total amount of fullerene. So we have two polymers and one fullerene. We did a systematic study of the total amount of polymer to the fullerene in the blend to determine how changing the concentrations in the blend of these three components influences the blend and how that influences the performance. So by looking at XRD, we found that there was a threshold required. So we have, for example, 20 and 30 weight percent. That means that the weight percent of these two polymers combined is 20 or 30%, and the PCBM is 80% or 70%. So when you don't have much polymer in the film, we found that the polymer was arranged amorphously. So we didn't form a semi-crystalline structure. And as a consequence, the charge transport through the film was very poor when you had this amorphously arranged structure. But as you increase the amount of polymer in the film for this three-component blend, we found, so from the XRD, we found that there was an increase in the crystallinity of this semi-crystalline polymer phase, and this was correlated with a significant influence or increase in the charge transport properties throughout the blend. So when we looked at the performance of the cell, we found that the optimum was obtained when we had a balance, when we had the same amount measuring by weight of the polymer and the fullerene. We found the optimum was achieved when we had 50% polymer, so we had a balance between the two. And this was because when we had very low polymer content, it meant that from the XRD we saw that the polymer arrangement was amorphous and we had poor charge transport. When we had very high values of polymer, it also affected the topography of the film, and the surface of the film was very rough, and that influenced the contact between the metal contact, the active layer and the contact. So we found that an optimum was achieved at 50 weight percent. How am I doing? And so then finally, very briefly, in doing this, the common way to form a ternary blend is where we have a wide bandgap polymer material. We try to sensitize it to longer wavelengths so we can increase the JSC. And we kind of put up with or deal with the fact that it's going to influence the microstructure of the film. But quite recently people have thought, well, what about if we can incorporate a second component which will have a positive influence on the film? How can we do that? What material combinations would we need such that that could be a reality? Recently we've looked at this material system but in reverse. So this is using silicon bridge PCPDTBT. It's the polymer we saw with the red one with the long wavelength response. We use this as the host system and then incorporated a small amount of this P3HT, the low bandgap polymer, which is a semi-crystalline polymer. It has a high crystallinity. And we found that doing this slightly influences the domain size. And from the IV curve, we found that incorporating a very small amount of this other polymer influences the film microstructure somewhat, and it led to a small enhancement of the JSC. So the mechanisms underpinning this are still under consideration or sort of future work to understand, but this is something that people are starting to look at now, because we can use, if we have a single active layer, then we can maintain the relative simplicity of processing that we've seen with the single junction cells already demonstrated for the deployment in the solar park. But we can potentially increase the absorption width of the polymer. There was recently, I'll say, a Nature paper published where they used a polymer called PTB7, and it's quite a high efficiency conjugated polymer. And they incorporated a small amount of another polymer into this amorphously arranged polymer and found that this had it had an influence on the phase separation within the polymer, and that led to actually a significant enhancement of the performance when related to the standard reference device without the second polymer. And they achieved efficiency of about 8.5%. So this could be a neat way it's currently being explored to try to overcome one of the problems of the narrow absorption blend by incorporating a second polymer. Now to the conclusion. The conclusion is largely based on the first part of the presentation. So what we've seen today, we saw that organic photovoltaic devices are solution processed, and this can lead to multiple advantages, including it could be very scalable, we have low embodied energy, and also we saw some examples of the flexibility achieved. The LCA analysis suggested that the embodied energy of these organic photovoltaic modules could be extremely low, pending the assumptions of improvements made for the future regarding the stability and also the efficiency. We've seen from last year multiple demonstrations that have indicated the viability of the solution process. It is possible to use all of these printing and coating techniques to fabricate modules and install them in the field. That's a demonstration from a couple of papers we saw from last year. And we also didn't neglect the perovskite technology. We've seen a significant improvement or rapid enhancement in the efficiency of that technology recently. And we've seen that it is compatible with all these things we've been talking about. The printing and coating techniques used to fabricate these organic solar cells, the perovskite technology is compatible with these technologies, and the efficiency is much higher. So the perovskite solar cells could potentially in the future utilize these kind of printing and coating techniques to overcome some of the key issues or the problems of organic photovoltaics. Thank you very much for your attention. That concludes today's presentation. I do have a list of references here for all of the papers I've looked at. If you're interested, I'm happy to forward those papers to anyone to have a look at the LCA stuff or the module deployment. I'm happy to forward that to you. Apart from that, thanks for your attention. If there are any questions, I'm happy to field. Thank you very much. Yes. Thank you.
Have you looked at, or anybody has published LCOEs of demonstrated systems, or any costing data that you can find on OP?
Costing, yeah. The cost, I didn't look at the costing analysis in this one. They had, I don't know if there is a holistic paper looking at the costing issue, OPV versus the other competing technologies. Within this paper, I did have a look, I think it's in the solar park paper. They do have a brief mention of the costs, and I think they used the example of a 1% efficient system and a 10% efficient system compared with silicon. Perhaps I should have put that table in, but it said that, so at the moment, we saw the system efficiencies of the organic photovoltaic modules very low, and the lifetime is low as well. So I think at the moment the cost wouldn't be comparable with silicon, particularly in the last 5 years when we've seen improvements for the silicon cost. So for these small prototype systems demonstrated in these papers, the cost, I can't give values, but would be not as low as silicon. If some of these challenging assumptions were executed, increasing the OPV efficiency to 10% and increasing the stability significantly, then they suggest that the cost would be lower than silicon, definitely lower, and the embodied energy would just be so much lower, order of magnitude or magnitudes lower. So at the moment, with the current installations for these prototype systems, it wouldn't be as cheap as silicon. But I think that if some of these challenging assumptions came true, then they suggest it would be. But that's, yeah, you're right, that's a good question. That was definitely something that I missed out.
Yeah, because I've seen 2 or 3 papers on OPV costing.
Okay.
They have a lot of assumptions, and
Yeah.
the assumptions are still lower than silicon. So I think it would be interesting to see the demonstrated system compared to those costing data.
Yeah, you're right. In that solar park system, it has a breakdown of the energy embodied, but it doesn't have a costing. You're right, yeah, I would have put that in if that was in there. Yeah, thanks for that question, that was good. At the back, yes?
Thanks for the presentation. You mentioned that the tandem cells are the highest efficiency OPV cells, and then the system efficiency of this demonstration is 2 or 1.5.
Mm-hmm.
So where does that drop come from? So say a single junction in the lab, like what's that? And so does the drop come from the scale from a lab cell to a large cell, or is it when you put it out in the field with all the accompanying ancillary stuff behind it? Where does the drop come from?
Yeah. It's interestingly, when we watched the paper regarding, the YouTube clip regarding the deposition of the perovskite layer using these fabrication techniques, they made a note of saying that all of these things are coded using ambient conditions. So the best OPV groups over the past years, the cell fabrication, the techniques in the laboratory are very different. So one thing is the environment that it's controlled in. Everything with the best groups, they have a glove box for every piece of equipment. So everything is a very much controlled environment. Additionally, the area of the cells is very small. So you see the highest efficiency cells, they're all on areas which are less than 1 centimetre squared. So that influences as well. So the fabrication techniques, the fact that the environment is so controlled and the size of the device is really small. So that's why this group is really trying to push and say that it's not, efficiency is important, but perhaps we need to focus more on, we need to do it in an ambient atmosphere using these techniques and be honest about where the efficiency is at the moment. So to answer your question briefly, the discrepancy is largely related to the processing conditions. Yeah.
So it's already low before you even start to put it in the system.
Sorry?
So, yeah, sorry, that's right. You answered my question. Thanks.
Okay, sure. Yes, Gavin.
Thanks very much, Matt, and a very nice presentation. On the ternary blends, I agree that the ordering is very important, and combining 2 polymers might improve that and get better crystallinity. Very important for the transport. But isn't that another very important factor that you've also got to have regions within the polymer sublattice, if you can call it that, which are small enough such that you've got an effective medium that can absorb the different wavelengths of the light. So that getting those regions, those domains of polymer such that they're small enough below, presumably the wavelength of light, is an important factor. Could you comment on that and what sort of sizes you might expect to have, say,
regarding the domain size of the polymers, or regarding the separation of the 2 polymers in the film? Is that? Okay, yeah. So I haven't included in this, we've also had a look at the vertical phase composition, which so we've used XPS, there are other techniques such as SIMS to show you how the polymers are arranged throughout the depth of the film. This was a pretty brief overview of what we've done, but looking at the XPS data, you can tell, well, you can sort of have an understanding about the phases together. To answer your question, it's still an area of research which is required, and I think that there are some other techniques which I'd like to pursue in the future to understand that. Thing like the Nature paper that I mentioned, which had PTB7 and PIDT as the second material, they used some small angle scattering techniques to try to understand the phase separation of the two polymers to understand the domain sizes. I haven't read that paper for quite a while, but I know that they do use those techniques. So using XPS or SIMS will give you an understanding of the distribution as a function of the vertical composition, but to really understand how the phases interact and the size of the phases will require more complex characterization techniques, and you're exactly right, that's what needs to be done now. So techniques like the small angle measurements, or also potentially it would be ideal if you could use electron tomography using TEM images to try to really understand, to build up a 3D image to understand really precisely the determination of the domains and the phases within the film.
I think that's very valuable for the overall structure of the bulkhead junction anyway.
Yes, yeah, applicable to binary blends as well.
What the whole structure looks like and where the percolation thresholds are and all those things.
Yeah.
That'd be really useful. Yeah, thank you.
Yeah, so the Nature paper was quite recent, and they were sort of the first one to investigate that phase separation using that small angle technique. Yep, you're right. Yes?
For the very long, 300-meter long strips, I assume that that's a single cell, is that?
It's all serially connected. I haven't, I guess I almost ran over time as it was, but there were a lot of other pictures I would have liked to put in. They've done a lot of work regarding the contacting scheme and trying to reduce the electrical shorts. And over the last 3 or 4 years, there's been multiple iterations of how to best do that such that you can have such a high technical yield over a long area, I think might be where the question was going. So they have the structure, sort of in the printing process, they have it's offset at a particular angle to optimize. So it's all these cells connected in series, heaps of cells connected in series. So it's very high, the system voltages are very high. They mentioned that, it's very high operating voltages from the system because there's so many cells connected in series, which is good for current losses. Is it dangerous? But the cell, I can, if you'd like, I can send you that paper. It has a really good picture of the structure that they use on the printing of the contacts, which is offset at some particular angle to avoid or to minimize the chance of shorts. Yeah.
More questions? So let's thank Matt again for a great talk.
Thank you.